Hi folks, welcome back to Physics with Captain Rod. Just starting that off with a little mood music here. So the purpose of this video is to demonstrate how to apply the theorem of work and energy when you have multiple forces involved. So what we're looking at here, we've got this 100 kilogram mass that's being acted on by the following external forces here. We've got this 400 Newton pound force acting kind of down and left, this 500 Newton force acting kind of up and left at angles of 45 and 35 degrees as shown. Assuming this starts from rest, we're going to try to calculate the distance this box moves before its speed hits 8 meters per second. All right, so let's do that. There's a couple different ways to handle this. You know, when I teach physics, I always point this out, that when you're talking about mechanics problems, there's two big methods to apply here. There's principles of work and energy and Newton's second law. And in a lot of problems, both are very applicable and work well, and this is one of those problems. However, because of where I'm at in my class that I'm making this video for, we're going to use principles of work and energy here. So what I'm going to do is I'm going to call this position 1. And after this box has moved a certain distance, it's going to be at a new location. And I'm going to go ahead and put that object over there. All right, I'm going to call this position 2. And then this box in position 2 is moving to the left, so I'm going to go ahead and put a velocity vector in here. I'm going to go ahead and put that in blue. And in this example, that v is going to be 8 meters per second. What we don't know in the picture is this distance here that the box has traveled. Right. Now, I'm going to go ahead and write out the work energy theorem, which says PE1 plus KE1. Right. This stands for the total energy of the system at state 1, plus all the work between 1 and 2 has to equal PE2 plus KE2. All right, and what I'm going to do is go through here kind of term by term. Now, this object is not moving up or down, and there's no springs or other non-conservative forces to worry about, so there's no potential energies that we need to worry about here. So I'm going to go ahead and put that to 0, set this to 0. Again, these can be anything we want, but by setting them to 0, I'm basically saying I'm putting a datum right through here. KE1 is 0 because this thing starts from rest. So all we're going to have is that the work between 1 and 2 is going to equal the KE2 term. All right, so now work between 1 and 2. The 500 Newton force no doubt is doing work, and so is the 400 Newton force, but there's other forces in this problem to consider. I'm going to go ahead now and kind of draw a complete free body here. In addition to those forces, we would have a gravitational force pointing down. So I'm going to go ahead and put that in here. mg. This surface, we have a contact point here that's going to provide a vertical force onto this box. That force will be up. Go ahead and I guess I'll put that right through my 1 there. All right, and you know, I'm actually going to go back and move that. That would have drove me crazy. Sorry, folks. All right. There's our normal force. And again, that's for the force vector along the surface. I'll put the 1 right here, position 1. Now, in addition to that, there's a frictional coefficient in this problem of 0.2 that we need to consider. If this box is sliding to the left, we're going to have a frictional force, which is going to be to the right in our picture. So that's what our free body is going to look like, something like that. And it's not done to scale. But all the correct forces, all the forces we need to deal with are going to be there. Now, forces that are doing work. This guy, not doing any work because it makes a right angle to the velocity. Same thing with the normal force, not doing any work. The 500 newtons is doing work, and we'll talk about how to deal with that in a minute. The 400 Newton force, that one's doing work. See how it's got a component to the left. This frictional force also is doing work. So there's 3 forces here that are doing work in this problem that need to be considered. Now I'm going to need probably a little more room here. I'm going to take this entire picture and maybe shrink it down a little bit. Move it up because I'm going to need a little bit more room to work here. All right, we're going to need this frictional force because it's one of the forces doing work in this example. This frictional force in this example is equal to 0.2 times the normal force, although I didn't state it. The intention was that the 0.2 was a sliding frictional coefficient. So we're going to need the normal to get that frictional force. We can get that from the fact that this object is not accelerating up or down. Now, I'll talk a little bit about how I know that. This object has a weight of approximately 1,000 newtons, mg, and this force has a vertical component certainly less than 500, and this guy has a vertical component down. So there's no way that there's a net force up on this object, and it's not going to bust through this surface and end up into the ground here. So this thing's not going to be accelerating up or down, which allows us to write the following equation. The sum of all forces in the y direction must equal 0. I'm going to go ahead and call up positive. And looking at this free body, that's going to be n plus 500 sine 45. And I'm going to do my standard NCU for note consistent units. All right, that's the vertical component of this 500 Newton force. Minus the vertical component of this force, which is going to be 400 cosine 30. Gravitational force vector, we're going to have minus mg. And that's it. The frictional force doesn't have a y component, so this equals 0. So in this example here, this m is 100 kilograms, and the 9.8 is the standard, 9.8 meter per second squared, or 9.8 newton per kilogram. And what we have here is an equation that, whoops, I got to go back just a moment. Did I say cosine 30? I was writing a force equation, y direction. This component of that 400 is opposite the 30 degrees. That would make that a sine 30, not a cosine 30. Okay. I think everything else is good here. So what I can do now is solve this for the normal force, and I'm going to keep that out of the video to keep this thing a little bit short. Put in numerical values here, solve it for n, and I get a value of 826 newtons. All right, so there's the magnitude of our normal. All right, we can now calculate the frictional force. So the frictional force is 0.2 times the normal. And that's going to give me a value of 165 newtons, if I did that right. And now we're ready to go ahead and calculate this work term. All right, so our work term, and there's two ways we can handle this. We can either do the work terms independently, or we can just add up the x components of all these forces. I think that's what I'm going to do. I'm going to find the net force to the left, and then just multiply it by distance. So that's going to look like, and I'm doing left positive, 500 cosine 45 for the x component of that force, plus 400 cosine 30 is the x component of that force, minus the frictional force, minus 165, and that's minus because the frictional force points right, and I'm doing left positive when I'm writing these, writing this force out for the work term, right? Times distance, so there's my force times distance equals 1/2 mv squared, and I'll just go ahead and put a numerical value there, 1/2 times 100 times 8 squared. That's my KE2 term. That's 1/2 mv2 squared. So this equation can be solved for the distance. And again, I was consistent with units here, so this is in newtons. This is in kilogram meter squared per second squared. So when I solve this for the distance, I'm going to get meters, and I get about 6 meters out of that. So this box is going to travel a distance of about 6 meters, and at that point it'll be moving at about 8 meters per second. Right? So again, the purpose of this video was to demonstrate how to apply Newton's, work energy. To do that, we had to draw a free body and calculate that frictional force. And then when we calculated the work term, this is very important here, right? Here's my work term. We are taking the x component of this force because that's in the direction of motion, the x component of this force also in the direction of motion. This force really only has an x component. It's in the opposite direction of the motion, hence the minus sign. and then times distance equals 1/2 mv squared. So again, the purpose of this video is to demonstrate how to use the work energy theorem in a situation where we had multiple forces in the plane. I hope that this has done that reasonably well. Have a great day.